In the name of God, the most gracious, the most merciful. This video is about series and parallel combination of resistors. First, we will discuss series combination. In series combination of resistors, the resistors are joined in such a way that there is only one path for the current to flow through all resistors. As you can see, suppose that current flowing through the resistors R1, R2 and R3 is I1, I2 and I3 respectively. As discussed earlier, there is only one path for the current to flow through all resistors. So, I1 is equal to I2 is equal to I3 is equal to I. Now if you look at the figure, you can see that there is not a single resistor which is directly connected to the battery, so the potential difference across each resistor will be different. Suppose that V1 is the potential difference across resistor R1, V2 is the potential difference across resistor R2 and V3 is the potential difference across resistor R3. Then by using Ohm's law, that is V equals IR, we can write that potential difference V1 is equal to current multiplied by resistance R1. V2 is equal to the current multiplied by resistance R2. And V3 is equal to the current multiplied by the resistance R3. So the total potential difference V will be equal to V1 plus V2 plus V3, or V is equal to IR1 plus IR2 plus IR3. Since the value of the current is same for all resistors, so current I is taken as common, that is V is equal to current I multiplied by resistance R1 plus R2 plus R3. Since current I is multiplied by the sum of the three resistances, if we shift it towards the left hand side of the equation, we get potential difference V over I equal to resistance R1 plus R2 plus R3. But according to the Ohm's law, potential difference V over I is equal to resistance R. So above equation can be written as R is equal to R1 plus R2 plus R3, or equivalent resistance Req is equal to R1 plus R2 plus R3, where Req is called the equivalent resistance and it is equal to the total resistance of all resistors connected in series. Now let us solve a numerical problem by using this equation. Suppose that three resistors are connected in series and their corresponding resistances are 2 ohm, 5 ohm and 7 ohm. Calculate the equivalent resistance. Solution. Since we know that in case of series combination, the equivalent resistance is equal to R1 plus R2 plus R3. Now let us put the values of R1, R2 and R3 in above equation. We get equivalent resistance is equal to 2 ohm plus 5 ohm plus 7 ohm. Adding these three values gives us equivalent resistance, that is equal to 14 ohm. Now let us review some key features of series combination of resistors. In series combination, there is only one path for the current to flow through all resistors. So the value of the current I for each resistor will be same. There is not a single resistor which is directly connected to the battery, so the potential difference V across each resistor will be different. In this type of combination, the total resistance will always increase as the resistances of the resistors are added directly. In this type of combination, the equivalent resistance Req will always be greater than the magnitude of the resistance of the greatest individual resistor. For example, here you can see that the equivalent resistance is equal to 14 ohm, which is greater than the greatest resistor connected in series, that is 7 ohm. Before moving ahead, if you found this video helpful, please like and share this video. And if you are new to our YouTube channel, then please subscribe. Now we will discuss the parallel combination of resistors. In parallel combination of resistors, the resistors are joined in such a way that each resistor is directly connected to the battery as shown. Suppose that the potential difference across the resistors R1, R2 and R3 is V1, V2 and V3 respectively. As discussed earlier, that each resistor is directly connected to the battery, so the magnitude of the potential difference across each resistor will be same. That is, V1 is equal to V2 is equal to V3 is equal to V. Now if you look at the figure, you will find that there are three different paths for the current to flow through the resistors. Therefore, the magnitude of the current across each resistor will be different. So the total current I is given by I is equal to I1 plus I2 plus I3. Suppose that I1 is the current flowing through the resistor R1, I2 is the current flowing through the resistor R2, and I3 is the current flowing through the resistor R3. By using Ohm's law, we can write that potential difference V divided by resistance R is equal to current I. So we can say that current I1 is equal to potential difference V divided by resistance R1. Current I2 is equal to potential difference V divided by resistance R2, and current I3 is equal to potential difference V divided by resistance R3. Hence the total current I will be equal to potential difference V over resistance R1 plus potential difference V divided by resistance R2 plus potential difference V divided by resistance R3. Since the potential difference V across each resistor is same, so V in above equation can be taken as common. That is, I equals potential difference V multiplied by 1 upon resistance R1 plus 1 upon resistance R2 plus 1 upon resistance R3. Since potential difference V is multiplied by the reciprocals of all resistances, if we shift this potential difference to the left hand side of the equation, we get current I over potential difference V equal 1 upon resistance R1 plus 1 upon resistance R2 plus 1 upon resistance R3. But according to the Ohm's law, current I over V is equal to 1 upon resistance R. If you wonder how, let me explain. We know that according to the Ohm's law, potential difference V is equal to current I times resistance R. If we shift this I to the left hand side of the equation, we get potential difference V divided by current I equals resistance R. Now, if we move this current I upward and potential difference downward, then we should also move R towards denominator. That is, current I divided by potential difference V equals 1 upon resistance R. Now, above equation can be written as 1 upon resistance R equals 1 upon resistance R1 plus 1 upon resistance R2 plus 1 upon resistance R3. Or we can say that 1 upon Req equals 1 upon resistance R1 plus 1 upon resistance R2 plus 1 upon resistance R3, where Req is equivalent resistance and It is equal to the total resistance of all resistors connected in parallel combination. Now, let us consider an example. Suppose that three resistors R1, R2 and R3 are connected in parallel and their resistances are 2 ohm, 4 ohm and 6 ohm respectively. Calculate the equivalent resistance of the circuit. Solution. Since in case of parallel combination, the equivalent resistance is equal to 1 upon resistance R1 plus 1 upon resistance R2 plus 1 upon resistance R3. By putting values of R1, R2 and R3 in above equation, we get 1 upon resistance Req equals 1 upon 2 plus 1 upon 4 plus 1 upon 6. By taking LCM, we get 1 upon equivalent resistance equals to 6 plus 3 plus 2 divided by 12, or 1 upon equivalent resistance is equal to 11 divided by 12. Since we are required to calculate equivalent resistance, so we move equivalent resistance upward and 1 downward. On other hand, this 12 should be moved upward and 11 should be moved downward. That is, equivalent resistance is equal to 12 upon 11. Now if we divide 12 by 11, we get 1.09 ohm. Now let us review some key features of parallel combination of resistors. In parallel combination, there are more than one paths for the current to flow through resistors. So the value of current I for each resistor will not be the same. In parallel combination, each resistor is directly connected to the battery, so the potential difference across each resistor will be same. In this type of combination, the total resistance will always be decreased, as in this combination the reciprocal of the resistances are added. In this type of combination, the equivalent resistance Req will always be smaller than the magnitude of the resistance of the smallest individual resistor. For example, if you remember, the equivalent resistance in case of parallel combination was equal to 1.09 ohm, which is smaller than the smallest individual resistance, which is 2 ohm. Our video ends here. See you in next video. Take care.